I think it's on now.
So, yeah, the next lecturer for this week will be Margaret Murnane from Boulder and Gilla, and she'll be talking about tabletop X-ray lasers.
Thanks so much, Andy and Leo. It's a real pleasure to participate in this summer school that Leo has been running for a long time now, and I can see why it's such a wonderful investment as a way to share knowledge and exchange ideas between the junior and us senior scientists. And today I'd like to talk about topics at the intersection of light science and condensed matter physics. The use of coherent short wavelength light to try to understand the insanely difficult topics that you are all grappling with. Of course, in any insanely difficult topic, if you can actually see what is happening, it is a little bit easier to compare theory and experiment. And so that's what my lectures this week will be about. And so using tabletop X-ray lasers to try to understand coupled many-body spin charge phonon dynamics. The other title, what we're really trying to do is figure out what are the good, not so much use cases, but where can a new light source help us understand materials and quantum interactions. And so we call this putting high harmonic quantum technologies to work. And because it's the intersection of light science, material science, and quantum material systems, we can't do it without a large number of collaborators. It's just nobody in a PhD or even in a career can just amass the amount of information one needs to actually figure some of these questions out. But as you can, the school really shows it is collaborations and interactions and teaching each other are where some of the really exciting things in science can happen. And can I do a little poll just to sort of figure out how much you guys need to slow me down as I talk? Who has heard of high harmonic generation? Who understands the physics? Hey, okay, well, okay, I'm relying on you guys to help me. But the other thing is, yes, so in the first, I'm glad I kind of got it right. So in the first part of this first talk, I'd like to talk about the physics. It was the subject of the Nobel Prize in Physics in 2023. And by understanding the physics, one can better understand what light source you need to answer a certain question in condensed matter physics or material science. And in this first lecture, I'll talk about something that's, I won't say straightforward, but it is using the coherence. So in other words, using it as a way to take things we do with lasers and extrapolate them to shorter wavelengths. Then hopefully it'll get more interesting in the talk tomorrow. We'll talk about nanoscale phonon transport. And there, if Leo agrees, I'd like to get help from a former student who's now at NIST, who's a real expert on phonon transport. And he can dive a lot deeper than I would be able to do on that topic. But then I'll be back Friday talking about the fastest things we can measure using this light source on attosecond timescales on up, and that are also intrinsic material properties. So not just making a measurement because we can, but trying to make a measurement where we can check a theory, learn something new, measure something better. And feel free to interrupt as I talk. Okay, so let's start with timescales. A femtosecond is to a second, as a second is to 30 million years, or a picosecond is to a second, as a second is to 30,000 years. So only spins and electrons can do anything on an attosecond timescale. No change in the crystal atoms can occur, but these short timescales can separate the physics of what the charges, spins, and phonons are doing. So in some cases can give insight even to the ground state interactions. So the ability to stroboscopically probe is useful, and it is very much needed these days. If we can now make things, multi-layers, hero structures, metamaterials and such, that are beautiful, beautiful nanostructures. But in every one of these cases, how heat flows, what the mechanical properties are, what the interfacial properties are, and how the spins and charges move are very different. You cannot use bulk models to, to model these systems. And so both for science and technology, we need better ways to look at devices, and by devices, I mean all the way from a simple, interface or thin film all the way to a full 3D device. And ideally, we'd be able to look at that in real time. There's no such microscope right now, but that's some of light science that I explore with my group. So why is this relevant? It is because extreme UV and X-ray light have wavelengths that are comparable to the nanoscale dimensions. They have elemental, chemical, and magnetic specificity, and this is because the core levels are characteristic of the atom. They're not hybridized in the valence bands. Because they're characteristic of the atom, you can track what atom you're looking at, or in an element, or in an alloy or a multilayer. You can tell its chemical bonding as well as its magnetic state. So it's a very powerful readout, and you also add time resolution, and you can suddenly see, for example, spin moving around if one is exciting material with light, for example, or generating a spin current or such. On top of that, because the wavelengths in the extreme UV and soft X-ray region span from perhaps 20 eV to a keV, those photoelectron energies, when you shine that on a material, are much, much softer than in a TEM or an SEM. So you can do a non-destructive probe or a non-destructive imaging of even a soft material. But all of that relies on the fact that, the high resolution imaging, or being able to take all the bandwidth and compress it into a short pulse. That is exactly what coherence means, that you can actually focus in space and time. And so we've known this since, ever since the DOE has been building beautiful synchrotron light sources. The problem has been that until very recently, we just couldn't make coherent light at short wavelengths. We knew how to do it in the visible for quite a long time. I'm holding a laser pointer in my hand. We've had coherence, or the ability to make a directed beam of light, since 1960. But it's actually shocking how slow progress has been in taking that coherence and bringing it to shorter wavelengths. You might not be aware that the first laser that was demonstrated was crimson, the ruby laser. And even today, the shortest wavelength laser in widespread use is the excimer laser. It's been around for longer than most of you have been alive. It's been around for many decades. It has a wavelength of 193 nanometers. It's used to print the less advanced circuits in our gadgets. And in 60 years, the ability to lower the wavelength of laser light has progressed by less than a factor of 4. And that's shocking, because in almost every other capability, our ability to compute, to store data, to do any other thing has gone many, many orders of magnitude. But this has been a real challenge. And the reason is that if you want to make an X-ray laser, that means you've got to, pump atoms into a very excited state. And they don't stay in an excited state very long. They tend to relax extremely quickly. So if you wanted to make a traditional laser at 1 nanometer, it would take more power than the total electrical generating capacity of the United States. So forget about doing it the brute force way. There were proposals in the Star Wars era, for those of you who remember what that is, to make an X-ray laser by detonating a nuclear weapon in space. Fortunately, that didn't happen, and let's hope it doesn't. And so that is why. So this is why these high harmonic sources are so interesting. It is the only way we know now to take laser light and bring it to shorter wavelengths so we can make, let's say, perfect microscopes or look at nanoscale processes. Okay, so it's a very interesting area of science. It was discovered by accident, or let's say not by accident. Charlie Rose and his group were trying to understand multiphoton ionization in rare gases. These intense femtosecond lasers were available only in the 1980s. And so people had to understand, well, if you shine a really intense beam of light on an atom, what is it going to do? And while they were doing that experiment, they suddenly saw that they saw 17 harmonics being emitted by the atom. So this would be as if you plucked your violin string or your guitar string and you heard 17 harmonics of the fundamental, all with the same intensity. This was really surprising. And a few years later, of course, people asked, how are they admitted? Charlie's funding program manager said, there's likely nothing new, just ignore it. But by 1993, people were seeing spectra like this. So this is seeing like 111 harmonics with roughly equal harmonics of light, of the fundamental laser light, with roughly equal intensity. And people knew immediately there must be some new physics because, like, for example, harmonics of sound, you expect the higher harmonic to get weaker and weaker and weaker. This was clearly not going on here. And so, yes.
So what was different in this experiment than the ones preceding?
Okay.
What did they do? That's no view.
They didn't do anything new. This is a universal response. So anybody with an intense laser that you can get to an intensity of 10 to the 15 watts per centimeter squared, 10 to the 14 watts per centimeter squared. This is a universal response of all atoms and molecules. I'll explain that here.
You irradiate gas with that laser.
Exactly.
Yeah.
And yes, I'm about to try and answer. Yeah. Thank you. So what is the laser doing to the atom? So this is a little cartoon of the electron. You can think about this as hydrogen. So an electron in the ground state, but exactly what Gio was saying. So what did you do different? Why was this not seen before? So it's because you didn't have a short laser pulse. If you have a short laser pulse, then with modest energy, you can get a high peak intensity. But the important thing is that the electric field of the laser has to be comparable to the electric field of the atom binding the electron in the ground state. You have to be able to depress that Coulomb field. So you create a barrier, and there has to be, if the field isn't intense enough, if you don't have enough intensity to distort the Coulomb barrier, you will get multiphoton ionization, which is what Charlie was studying. If you increase the intensity above that, then you depress the Coulomb barrier, and suddenly the atom undergoes tunnel ionization, and you don't have to, as I'll show you in a movie, you don't have to ionize, you don't have to pull all the electron wave function out in one step. You can do this on multiple steps because the electric field of the laser, of course, is changing sign. during the pulse. And so what you will, you will do this every half cycle of the driving laser. So you will get a periodic emission in time at the frequency set by the frequency of the driving laser, and do the Fourier transform in your head. And if you get period in time, what do you expect the emission to look like? Peaks, exactly. That's exactly what the harmonics are. They are just peaks due to this. You can think of the electron moves, well, once ionized, then of course that electron finds itself in a field of the laser that's comparable to the Coulomb field binding the electron to the atom. So it's going to move away. And when the laser field reverses, it'll come back. Some fraction of these electrons will recombine and you'll get harmonic peaks. And so you can think about this as multi-photon, as a combination of an odd number of laser photons to make a harmonic, but it's a little bit, it's beyond multi-photon ionization because, and I'll explain later, of while the electron is in the continuum, it acquires a quantum phase corresponding to the action integral. So it's a very quantum phenomena. That's shown here in this little movie. You can think about this as a 2D representation of the electron in the ground state of hydrogen being perturbed by the laser field. So it starts out in the ground state of hydrogen. Then as the laser field gets strong enough for the atom to undergo ionization, you can see this is actually what this boomerang trajectory actually looks like in 2D. And the wonderful thing is that because the acquired phase on the electron wave function is different from the part of the same electron that's still in the ground state, you get these beautiful quantum interferences. And so let me run the movie one more time. So this frequency is the driving laser frequency. Is that right? So that's your driving laser. But the frequency that's emitted, so this is the quantum sort of origin of the harmonics, is related to the time-dependent dipole. And because of the modulations on the electron wave function, it looks like you're accelerating that electron at much, much higher frequency than the driving laser frequency. That is the actual origin of these high harmonics, that you're actually turning the atom into a nanoscale quantum antenna. And in fact, this was actually understood very early on. Charlie first observed high harmonics in 1987. Ken Kuhlander had already written down the time-dependent Schrodinger equation with the continuum state, back in 1992. And then people began to sort of get intuitive understanding later. So what's going on microscopically? You've got the atom undergoes first tunnel ionization, then propagation in the field, then another dipole recombination from a continuum state back to the ground state. And then that is the, from this displacement, one can calculate the acceleration and then the time-dependent dipole moment. And so that's what that is sort of the quantum origin of high harmonic generation. And the very nice thing that one can use to one's advantage is the quantum phase acquired by the part of the electron wave function in the continuum. That can be many, many, many times pi. So you can actually do quantum manipulation of the radiating electron wave function. So it's, this is sort of why this is a very popular topic, because you can write down a lot of things from a lot of the physics from a classical point of view. One could do relatively straightforward 1D quantum calculations on the radiation from a single atom, it gets much more difficult if you have to consider a whole bunch of atoms and adding the emission together. But these days, early on in the field, just like in condensed matter physics, the available simulations were limited, but it's getting with more powerful computers, one can model the experiments more and more accurately these days. The other thing you can do is you can mess with the polarization, because I just showed you this movie that's what happened if we use a linearly polarized laser to excite high harmonics. Now, of course, for many spectroscopies, circular dichroism and other probes, one would like to have a circularly polarized harmonic. But the problem is if one uses a circularly polarized electric field to ionize an atom, it will ionize, but of course, because the field is circular, the electron will never return to the atom. What happens if the electron doesn't return? There's no emission because you can't make the dipole transition to state. So for about 20 years, nobody made circularly polarized harmonics. Becker's group published but the paper had 2 sides. None of the experimentalists read it. And Wilhelm, was a strong field physicist. He didn't understand how much magnetics, for example, needed, and so it was a great example of, the solution was there under our noses. We could even have searched for it. But anyway, Oren Cohen and our group rediscovered this. And so the solution is, let me see if I can start the movie, is if you use 2-color counter-rotating fields, you can actually ionize the atom and the electron returns. So this is just very beautifully, modifying the radiating electron wave function. And there's even a nice intuitive sort of way of explaining this, that we know you can sort of think about in energy, high harmonics just corresponds to just adding up an odd number of harmonics to get all the different harmonic orders. Now, if you give them spin polarization, because the emitted high harmonic photon can only have 1 unit of spin angular momentum, you can only grab 1 more or less photon from, let's say, if you use red and blue, and in that way make very nice sculpture the polarization. Yes.
The high harmonics will have like opposite.
Will have opposite. In fact, you get pairs instead of each odd order. You get odd pairs where each pair has left and right. It's a really strange spectrum you could not make other ways at each frequency. And then some you can resolve it in a spectrometer. So you can shine it on a magnetic material, disperse later, and you can do UV circular dichroism measurements. Yeah.
So after you generate the higher, make it circularly polarized?
Yes, and you can even do more crazy things. I had to limit myself here because I want to get to something that, some materials physics, but you can do things like if you mix different OIM orbital shape, if you mix shape and polarization, you can actually get the beams to go out in different directions. And you can, this is kind of why you will, if you Google, you will see a lot of papers, because people are just beginning to realize how well you can tailor that light. And it is useful to be able to do that at the source, because X-ray optics are not anywhere near as developed as visible optics. So you can't get many optical elements, and when you can, they're very lossy. And can you imagine, it's hard enough to get a good flatness optic in the visible, but can you imagine if you go to 1 nanometer, just the difficulty in just polishing the optic is really hard to get the same. For example, if you want a 10th wave optic, it's like impossible. So it's very nice to do as much as we can in tailoring the source itself.
Generation of certain parts harmonics first just using linear light and then like some wave plates or something generates.
If only we had a way. Optics just don't exist. You can do it by very lossy ways, you can use mirrors, to change the polarization, and you can actually make a wave plate, but they're not commercial, and the throughput might be 5%. And if you want good signal to noise, you don't want to use these fancy lasers to make the light and then lose most of it before you put it on your sample. And for circular polarization, one of the applications, of course, is for I will show an example actually at the end of this talk in imaging a 3D spin texture. Yeah, so there you do need to use magnetic diodes. So you need to make left and right circularly polarized. That particular experiment had a synchrotron, but uh-huh. Yes.
You get an even number from K, let's say 6 omega, and the total angular momentum becomes 0, or?
So the angular momentum of a photon has to be plus or minus 1, the spin angular momentum.
Linear for.
Then you would think about it as equal combinations. Yeah, you can always, yeah. So you can do, said before, if you add in orbital angular momentum, so the shape, and then the combination, the selection, one can get way more fancy than this, but this is, you don't want to go through a bunch of selection rules on light at the school. Yeah, but yeah, there is a lot in the literature on this. Yeah.
Yeah, I was trying to understand the relation of, you shine very
Colors.
intense.
Yes, so we just shine two, not very intense. This would be, you can do this with less than a millijoule. In terms of femtosecond lasers, a millijoule is nothing.
No, but I'm missing something. So first you talk about the ionization, near
Yes.
ionization.
Yes.
The short pulses and generating these. But slide, you now have an IR laser. No, next one.
Oh, yes.
To say,
Well, thank you.
what's the
Thank
relation
you.
of this to the first thing?
This is now how we sculpt the spectrum.
So this is in
This is
addition,
a
you
new-
also have an IR signal.
Actually, you can use any color, 1 color, 2 color, 3 colors. We've done all of it, shining onto the same atom. Because if you want to take advantage depending on what light you want to make. So we have a lot of recipes. So we have intense laser light now from, let's say, 200 nanometers up to the mid-infrared. You can choose any of those colors to make harmonics with, and the harmonics come out a little different. I'll explain that here. And then you can shine more than 1 color to get both, to change the shape of the beam or the polarization of the beam. It's all based on selection rules.
Is the IR an additional laser?
Yes, so we have UV lasers, visible lasers, near IR, mid IR, and we use them all. For the most, we use different combinations. We've got different lasers to make different types of X-rays for different applications. Exactly. So the laser one would use, thank you for this question, because it was something I was trying to get across. The laser that would be best to use for an RP's experiment is different from the laser that would be best to use for magneto-optic Kerr effect experiment, is different from the laser one would like to use for imaging. So it just really depends on what you're trying to do. Yeah.
What is the intuition of what parameters control how many harmonics you get? How broad is it?
This is exactly what this is about. And in the next 3 slides, I hope to be able to explain that. Yes. doesn't matter that much. Yeah. It turns out that for this exact reason, and can we talk again after the next 3 slides and then I can explain and okay, and it's actually it's related to this this wave, and I'll come back and talk about the topic. All the ionization happens here. Why? Why would the ionization happen at the peak of the laser field? What do you think? When do you think the Coulomb barrier is depressed the most? Then the electron moves away and comes back, and the emission happens around here. I'm being very non-precise here, but it's better to get an intuition because then you can read the paper. So the electron emerges here and recollides here. So there's these little bursts, and this is what the Attosecond science, you make these bursts because each one is like a coherent Bremsstrahlung because you pull the electron and then out and then it returns.
No, that's IR. I just want to understand.
Same thing happens for
You're
UV.
getting X-rays?
Oh yeah.
Even with an IR laser?
Actually, the IR lasers work better to make the shorter wavelengths.
Okay, as long as it's true, all you need is just that it's strong enough to ionize. So
Yes,
you get this non.
Exactly. And every atom and molecule exhibit this exact same response, this ionization, we call it the, trajectory in the field and then this return. So you can change the color, and that's like changing the score. If you change the color of the laser, and it does change the X-rays that are emitted. Absolutely.
But it's still X-rays.
Well, they go all the way from the vacuum UV to the soft X-ray region. And for different applications, you want the light in different regions. So what our field tries to do is figure out what laser is best for what particular color you're trying to make for a different application in condensed matter or material science.
How do you get back to the simple limit, like where what's emitted is, just
Harmonics?
Like you hit it with IR, you get IR plus a couple of harmonics. You just have to let that.
Turn the intensity down. Yes, this is strong field. Absolutely. You have to be able to depress the Coulomb barrier for long enough that there's some finite probability part of the electrical function can tunnel ionize, because that's related to how much dipole recombination you can get. So it would be super weak. And anyway, so it's related to the tunnel ionization probability compared to the multiphoton ionization probability. If you're at low intensity, tunnel ionization is so weak that probability is really low, and multiphoton ionization has a higher probability. Does that make sense? So there is exactly an intensity threshold.
That's the same thing as high harmonic generation.
No, multiphoton ionization happens is the most probable, which is ionization without distorting the Coulomb field. So that's a more traditional nonlinear optics, or sort of, yeah.
Okay.
Yeah. So now I will try to explain if you change the color of your driving laser from ultraviolet to visible to near infrared, how the harmonic color will also change. And it's related to that, for any application in condensed matter, if it's RPs or imaging or XMCD, and such, you need enough photons so that you can make a good measurement. And what that means is that the emission from many atoms, in some cases, to get bright emission, we need to add the emission from the same number of atoms as there are people on Earth, and do that coherently. Doesn't sound too bad until you realize that this is not drawn to scale. And say if my laser was a 4-micron laser and I was trying to make a 1 nanometer X-ray, and I want all these emissions from all the atoms to add coherently. Now, this is a stupid question, okay. So if I have a 1 nanometer wave, and I want to add it coherently to another 1 nanometer wave, how precise do you think I need to align those waves up? Nanometer would be good enough. No, it has to be small fraction of your wavelength, is that right? And in time, a 1 nanometer wave corresponds to a frequency of about an attosecond. So you would need a modulator that can align up waves to less than 1 angstrom spatially and less than an attosecond temporally, and they don't exist. And we are very lucky that nature does this passively. We don't need to we do it anyway. And so what does it do? So who has done frequency doubling with the laser? You know, taken the output of a laser and okay, so thank you. So you know that if you put a crystal in front of your laser, if you don't put the angle right, you don't get any frequency doubled output. And so we call that birefringent phase matching, or phase matching in the spatial domain. So harmonic generation and its quantum physics were all discovered in the late 80s, early 90s. It took until about 2012 to figure out phase matching, because it was only because it was conceptually different that the phase matching, or the time window in which you can add all the waves in phase, happens in the time domain. And it was so conceptually different that, and anyway, people were attending different conferences. The optics people were going to one conference and the atomic physicists going to another conference. So it was like two different fields for a while. But now we know that what happens is, as your laser light is propagating through the medium and ionizing and generating harmonics from atoms, you know, along its trajectory, if these waves are going to add in phase, the laser light and the X-ray light better be traveling at the same phase velocity. We know this doesn't usually happen because, you know, a prism disperses light because the red light travels faster than blue light, so gets so you separate the colors. But it turns out that when the laser is weak, so early on in the pulse before the medium is ionized, the laser is traveling slow, and any X-rays that are generated are traveling at the speed of light in vacuum because the resonances are so low and that X-rays don't bend. Nothing bends X-rays. So the refractive index, the index of refraction is 1. So the X-rays always go at the speed of light in vacuum. But in an unionized gas, it looks like a very thin piece of glass. So the laser light slows down. But in a plasma, the phase velocity of a laser is greater than c. So while you're ionizing the atoms, both the laser and the X-ray light are both traveling at the speed of light in vacuum. And that's where you get phase matching happening. So, and that is essentially what gives us the ability to tune the colors that come out and what the spectrum looks like. If you use a Ti-sapphire laser that some of you may be familiar with, there's a large time interval, multiple cycles over which the laser light and X-ray light travel at the same speed. So you get a nice spectrum. You would recognize these as harmonics. But if you use a mid-infrared laser, they're only 1/2 cycle. So it's one coherent recollision. The advantage is that that phase matching extends up to a keV. So, so you get to tailor the type of light one makes by tailoring. In this case, it's the color and the phase matching, but there, I told you about other ways you can also do by tailoring the shape and the polarization.
Light and X-ray, what's the difference?
So the laser is the visible laser like the screen or Ti-sapphire. So it's something you would buy, say commercially, or build yourself.
X-ray is the thing you want to generate.
The X-rays, the harmonics are the things we're trying to generate and trying to learn how to control their properties so we can make good measurements. Right, and that is actually a picture of a 1 nanometer high harmonic beam that looks almost as good as a laser beam. And it is as good as a laser beam. In fact, when I want to get a rise out of my laser colleagues, I will claim that we have better control over light in the X-ray region than we have in the visible. In the visible, we're very much dependent on laser gain media and optics, whereas with this harmonic process, if you can sculpt the radiating electron wave function, you have way more control over what you're generating. But anyway, okay, so this is this crazy, there's too much on this view graph, but the thing I'm trying to convey is that we can control whether we make an isolated attosecond pulse or a pulse train. We can control the shape. We can actually make a pulse that changes its shape in time due to this crazy selection rules. We can adjust the polarization. We can make a single harmonic or a super continuum. This is really handy because, you know, for electron spectroscopy, you would like to have a pure color so that you can read out the electronic structure. So this ability to sculpt, you know, is quite important. So now,
Really sculpt, you're not like
yeah,
doing the first and then filtering out.
no, we're sculpting. In a lot of our experiments, we don't have to do the fanciest things, but I think some of the physics is very interesting that you can sculpt. That's a lot of the ongoing physics. So even though for the most advanced sort of light science sculpting, we wouldn't put that with a hard application because that's a recipe for a very miserable PhD degree. Because to make measurements, you need stability. But the light science is super interesting. Yes. So turns out helium is the best one. Any noble gas is good. People played a lot with diatomic models to try and see if the returning electron could actually map the orbital. That hasn't, I mean, we'll still do experiments, but it turns out if you want to do a hard application, you just want to use a noble gas. They're hard to ionize, they've got high ionization potentials, and I would say 90% of the work is done with those. And, this audience is super, will understand this point that, in terms of understanding nanoscale processes, it's very hard to develop comprehensive theories if you can't validate. And so this is where sources like high harmonic generation or ultrafast X-rays from X-FELs or synchrotrons can, help get some data to see, are we understanding the materials well? What we'd really like to do is to image heat and spin and charge inside a quantum or an energy device, look at a wave function propagation, or image living biological cells, for example, at the molecular level.
Sorry if this makes much sense, but my interpretation is that you have to get a short pulse, you need many colors.
Yes.
And with so you need a large bandwidth, but to get these attosecond pulses, you must need a lot of colors of X-rays.
I'm gonna deal with this Friday because this is related to the uncertainty principle and how do you make a measurement. But I'll give you a short answer now. In the field of, let's say, femtochemistry and femtosecond science, if you continue to make the pulse shorter, you can get to 10 femtoseconds and still make good measurements, because if you apply the uncertainty principle and ask what bandwidth you need for a 10 femtosecond pulse, that's about 1/10 of an EV. So you can still resolve band structure because, there are only so many things that have real physics on attosecond time scales. They're almost all in condensed matter, and they are almost all band structure dependent. So if you ask what bandwidth you need for an attosecond pulse, that's a kV bandwidth. That spans multiple bands. You will be able to see things, but my claim is you can't see anything intrinsic because you're not measuring the actual, and it's only charges and spins.
The bandwidth to generate these attosecond lasers is coming from all the harmonics.
Yep. Yep. So and depending on how you make the measurement, you're using different aspects. So it turns out that, I mean, if I put this in hierarchy, so the 0th order use is you've got a coherent beam. Forget about the time structure. You can do coherent imaging now and see things. And then you can start to use the time structure. That's what Brendan will talk about tomorrow, and looking at phonons. And then I'll talk about on Friday, looking at really fast charge and spin scattering processes where you have some sub-femtosecond dynamics, but you can still see. You have to be careful how you make the measurement. Chemists went through this back in the early 1990s. There's a whole decade where almost every paper that was, I'm joking here, was wrong, because people were using what's called a transient absorption spectroscopy and trying to match that to a model, but so many measurements would look the same for different models. So it was very hard. And when they moved to what's called multidimensional spectroscopies, then you could actually figure out what was correlated and what was not. So this is why we talk about your measurement science, how you make the light, how you control it, how you make the measurement so you can make a good comparison with theory. Okay, yes,
Sorry, so I still want to understand, so you're driving with the short pulses,
yes,
you're generating these many
yes,
harmonic.
yes. The laser, little up converter, and then you make these beams that are coherent.
What comes out,
Is a beam.
are they also short pulses?
Yes,
How
but
short are those pulses?
oh, ridiculously short. I mean, we make pulses. We even have a paper that has it's a theory paper, but it's a generation of zeptosecond pulses, 10 to the minus 21. But because, if you can control the waveform of light, you can control a broad frequency spectrum. And of course you can make a short pulse. I'm going to try to convince you, you almost never want the pulses, the short pulse, but you want to control the spectrum and the beam.
But you don't want it to be that short.
No.
That it could span, EV.
It depends on what you're measuring. So as a backlight, for example, for a charge transfer in a, let's say, photovoltaic, the supercontinuum are fine, but they're not very good for RPs because you would just smear all the bands together. So it depends what you're trying to do.
So you might back off and not make them so.
Actually, what we would do is make them the way they want to come out, because you can't mess with the phase matching. That's just the way that happens. So if they come out as a supercontinuum, just live with it, but then take a multi-layer mirror that we can make at different photon energies and take part of that spectrum and use it like a tunable X-ray laser. So that's more the I would say the useful applications. Uh-huh.
Afterwards.
Oh yeah, before or after, absolutely. You can shine them all on a material, like we do that with resonant magnetic scattering. You take a supercontinuum, shine it on your magnetic material and just collect the part of the light that scatters, and essentially the experiment does the separation. Yeah, so it really depends on, there are so many ways to set it up. Yeah, but most of what we do would not need an isolated attosecond pulse. And in fact, I'll explain Friday how it actually wouldn't work. So yeah, but we're getting ahead of ourselves on that one. Okay.
Yeah, the width of the pulses are bandwidth limited, like you generate this enormous bandwidth, but the pulses,
They're chirped
they're chirped.
to a femtosecond. So you have an attosecond bandwidth spread over a femtosecond. But in most of the things we're measuring, you see anything in condensed matter, any coupled charge phonon dynamics won't be very fast. All right, because the lattice can't move. Now, charge spin can be very fast. That can be just a photon, so you can move that. Electron scattering can be fast. So there are certain processes that are fast, but most are not. So that is sort of a misconception people have sometimes, that the shorter the pulse, the better. And I would say attosecond pulses come out of phase matching. You need to phase match to make a coherent beam, but you don't want such a short pulse. It's useless in many cases.
But so if you take your bandwidth and make the shortest phase match pulse, how short it will be?
It would be a femtosecond because you have to correct the chirp to get an attosecond, and nobody's ever done that because there's absolutely no application.
If you can out of pulse.
Oh, it has been measured. We've measured ourselves. I mean, people have been measuring, and we have attosecond pulses since late 1990s, but they didn't get used for things because there's nothing except electrons. I mean, I have nothing against electrons, but it's electron screening of interactions is a much more interesting question than electron scattering, all right? Because that people can calculate that. Anyway, I'll pick one application and but we have to do all our applications with experts because we don't know enough within our own group to either make the samples or know the interesting questions. So all the work I'll talk about, we've done in collaboration with other people. And what we want to do is now use this harmonic light source as a coherent synchrotron, as a ultra-fast coherent synchrotron, where we can look at the magnetic properties or the transport properties or the structural properties or elastic or compositional or electronic properties. And of course, this is a big field, so there's a lot more work than in our own group, but these are the slides I have. Okay, so in the last, I have time. Oh, great. Okay, great. I thought I went too slow. No, great. So, would like to start with discussing an application that does not use the time structure at all, that just uses the fact that we can make, a coherent beam that's directed, but now at shorter wavelengths, and make a better microscope. And it turns out that all modern microscopes, like the most advanced electron microscopes or light-based or X-ray based, they're not like the microscopes we used in high school where you would, peer into an eyepiece and see an image. You have to use an algorithm to actually recover the image. The image looks very blurry, and only when you apply these fancy algorithms can you see the image. And so that's what I'm part of a Strobe Science and Technology Center where we're trying to push the frontiers of both electron and X-ray imaging, and advancing both the algorithms and the actual microscopes and the light that we're using to illuminate them. Okay, so the reason coherence is so important, spatial coherence now I'm talking about, and the reason it's so important at short wavelengths is that there are no good short wavelength lenses. As we talked about before, no material bends X-rays, so you can't make a refractive lens. So you have to use a diffractive optic that's called a zone plate. And the spot size one gets if you focus X-ray light with the zone plate is totally limited by how good you can make that zone plate, totally limited by E-beam fabrication. And so the best microscopes are typically X-ray microscopes. If you try and use the traditional approach, are typically 10 times diffraction limited or a 10 times bigger spot size than the wavelength of the light. And all that changed between the second half of the last century. David Sayre in 1952 proposed using coherent light as an illumination, in which case you can throw out the lens. And our collaborator Jian Miao demonstrated this in the 1999, and believe it or not, David Sayre was a co-author. So sometimes it can take 50 years for the technology just to catch up. So what's the idea? So the idea is, if you have a coherent beam of light, you could shine it on an object, pretend it's a cell or something like that, and you're going to get scattered light. And in a normal microscope, you'd stick a lens, an image forming lens into the microscope and you read out your image on your CCD camera. If instead of sticking the image forming lens in, one feeds the scatter pattern into what's called phase retrieval algorithm that are used ubiquitously in science, you can actually recover the image and there's no optics between the sample and the detector. So that means there's no aberrations. So suddenly you went from 10 times the diffraction limit to just numerical aperture. So instead of 10 lambda spatial resolution, you can get to lambda over 2. So that's a big deal in X-rays because it really improves the spatial resolution of the X-ray microscopes. So how does it work? Oh, sorry, this is David Sayer's full paper from 1952. God, it is really frustrating to see that now compared to what we do now with the papers and the SIs and whatever. And not only that, look at his last line. The extension to 3 dimensions is obvious. I mean, no reviewer would let us write that these days, isn't that right? We'd be killed. Anyway, but yeah, so John got David Sayer on his paper in Nature in 1999. So how does it work? How do these algorithms work? Well, initially they didn't work very well, and in fact, it was a viable imaging technique. Because initially the algorithms and compute power were much limited. So what we do initially was, for example, we did a little hole in a piece of metal with J for Jilla. You shine the UV beam on it, get a scatter pattern. You need to do a Fourier transform, but you have no idea what the phase is. So you just assign a random phase, do a Fourier transform, and in the initial work, the sample had to be isolated. So that meant anytime you guessed the wrong phase, you would get some crud around the image. You could zero because you knew it was due to incorrect phase. Then you could take a Fourier transform and then replace the intensity of the Fourier transform by your experimental data, but your phase now was better than the random guess. And you would go around the loop until it converged. And these initial algorithms were not stable. So what people did, they would run the algorithm 200 times. Then nobody believed it. Real scientists want the average image of their sample. They want the actual image of their sample. And so these days, the data handling and algorithms are much more powerful. What we do is scan the beam over a sample, but have a lot of overlap between adjacent scans. And now that forces that redundancy. This was developed by John Rodenberg and Thibault and Maiden. That redundancy forces the algorithm to converge. And this really, now every FEL and synchrotron being built worldwide, and also with tabletop and also with electron imaging, are all using this approach. It's called tychography. And it really works. And when you combine it then with the high brightness synchrotrons, the XFELs and the high harmonic sources, we can show that we can measure a lot of different things. And in particular with the extreme UV light, for looking at heterostructures, it's really nice. Those of you who might have seen images from a synchrotron in the soft X-ray region, soft X-rays don't, the index is low, and so you don't get any reflected beam. So all the microscopes work in transmission like a TM microscope. The extreme UV still reflects. So you can make a microscope where you can take a part of a heterostructure, or, magnetic multilayer, and stick it in your microscope and still get a reflection. So we can build a microscope. And then if we have a coherent microscope, we get to separate different materials by their reflectivity and also by their phase change on reflection. So suddenly you get a lot of information that you can use to build a model and learn structure looks like. So these microscopes work like this. We have to take the data at a number of angles because fast, and then at each angle we do a tychography scan and then build a model. And we were fortunate that we got some very nice samples from colleagues at EMEC. This just happened to be, it was complex. We needed a complex sample with different heights and different doping, and could we see under buried layers and things like that. And this was a good sample to use. And so this is model based, but you can then extract a map of the surface where each color is a different material, and then a sort of an in-depth what is under your surface. So this is the top layer, the SiO2 passivation, silicon nitride structures, and then silicon with the arsenic dopant underneath. And we can do that in different regions of the sample, be able to, again, with a model based, this was this is a PhD thesis. It's not a commercial instrument. This is just exploring, what can we do with this light source. What's interesting also is that some collaborators at 3M were making polymer metamaterials. They can be used to coat as anti-reflection coatings, for example, for solar panels. We would like to gather as much of the light as possible, but they're tough to image because the way they work is that they're made out of plastic, very complex structures. They have to have little holes that are smaller than the wavelength of visible light, so you can't use a visible microscope. And if you put it in a scanning electron microscope, the high energy electrons tend to partially melt the polymer metamaterial. So that was the challenge we were trying to overcome. And sure enough, we showed that we could actually distinguish different samples, get a very clear signature, because of course, the wavelength of our light is tiny compared to the size of these structures. So it's like with any kind of interference phenomena, if you've got, you have a lot of measurement capability, if you have many wavelengths to play with. Yes.
This light is less destructive just because you put in less energy to the material?
Photon energy is only 30 EV compared to the multiple keVs in an SEM. So 30 EV makes a photoelectron of about 25 EV, and that does pretty much no damage. Yeah. And of course, we had to validate this. And so we worked with Steve George's group, who is measurement in a transmission electron microscope, where if you do conformal atomic layer deposition, so do a couple of nanometers of deposition over the metamaterial, as well as deep into its structures, before you coat them for you can preserve the structure. Great for a validation, but it's not a practical metrology. But we were able to show that we got the same results. Yes, of course. So this is scatterometry. We are doing averaging. So this is, because this is very fast. We can do this measurement in 10 minutes. So all it is the diffraction efficiency from this 2D grading as a function of angle. And just showed that they gave us two different samples. They wanted to see if we could distinguish them. And then we had to do this conformal TM to tell them what their sample looked like, because actually you can't, with the SEM, you sort of partially melt it. So they didn't even know what the sample looked like, because they're very complex structures. They look like little holes here, but they're multiple layers. So they're quite. And what I forgot to say, the scatterometry is actually very powerful. It can tell you about what the layers are, what are their density and what are their shape. That's why you do it as a function of angle, so you can build a model that then has good error bars. Oh, here, it's really just the spot size, so it's 5 microns or something. So here we're not trying to do imaging. This was a different question that we were, in the previous one, the spatial resolution was 60 nanometers. We've done as high as 10 nanometer resolution, but in many cases, the absolute resolution is not the question. It's like, you know, the questions are like here, what did the sample look like in terms of its gross, its overall shape? It's very hard to do process control if you make something and test it in the application. And so there's a lot of, and this is the same thing, of course, for science. If you make the material and then often, and integrate it, either in science or technology, if you just test the integrated system, you really don't know if it doesn't perform well, what is wrong. Is it the interface? Is it the doping? Is it, what is it? This is just some fun light science. So I've been telling you how good coherent imaging is, because we can make a near perfect light X-ray based microscope. But there's one place where it fails miserably, which is if you have a periodic structure. And the reason is shown here, that if you have a periodic structure and you scan a Gaussian beam over a periodic structure, so what are you seeing? You see the Gaussian beam, the red, and it's scanning over the periodic structure. Well, what do you notice about the diffraction pattern? It's not changing because nothing is changing. And so the algorithm has nothing to work on. But if instead we use our selection rules to make a donut-shaped beam, like the beams that are used in, STED microscopy, now when you scan that beam over the periodic sample, you actually, the diffraction pattern changes. So now the algorithm has something to work with and can actually retrieve the image. Here, it was a perfectly periodic 20 nanometer thin carbon grid. We could see the defect. And when we tried to look at the same, little scratch with an SEM, the SEM started to drill out the little 20 nanometer thin grid. And that was part of the PhD thesis of Ben and Nathan. And here they are at Arapahoe Basin the day after they, got their PhD degrees skiing in their regalia. They got a lot of high fives on that. Okay, finally, sunken S matter. Okay, but actually static. Okay, so one thing that we've been trying to do is developing new techniques to measure properties, structure, and function. And magnetic skyrmions there's a lot of activity in this area because of the possibility of making lower energy consuming devices, because the skyrmionic systems are partially topologically projected. And so people look at these skyrmion with magnetic force microscopy or small angle neutron scattering or Lorentz transmission electron microscopy, or Peter Fisher has looked at a single skyrmion and then milled out the single skyrmion disk and then imaged it at the advanced light source it would be wonderful if we had a way of imaging and actually dealing with the of the full 3D dynamic spin texture. Not anywhere being able to do that, but we started with trying to make a general way of imaging a 3D spin texture. And so, and most of these are not compatible with good time resolution. So, or they don't have 3D capabilities. So we started on a simpler topologically protected material than skirmion. So it had been predicted by Vin Crespi and Hahn back in 2002 that if you made a frustrated magnetic system out of magnetic nanodots, where the dots were connected and their spacing was on order of the exchange length, that should freeze in some magnetic texture that should be topologically protected. And they call these, hedgehogs and anti-hedgehogs. And I was talking to Han a few years ago, and they said, they wrote that paper. They weren't even careful about the models because they never thought anybody could ever measure it. But he was just joking. I mean, it was impossible to measure, and we didn't have as much compute back then. So it was. So anyway, so we got together, and John Badding made a nickel metal lattice structure, and we stuck it into the coherent imaging microscope at the advanced light source and used some algorithms that could actually give us the 3D spin texture. And here, this is one example of where we use polarization structured light. We use either left or right circularly polarized X-rays. And for each one of those polarizations, we need to make a tychography scan. Then to do the tomography, we have to do tomographic scans. And to get the full tomographic and 3D spin texture, we need to do 3 tilt planes. So this was a lot of data. This experiment was done during COVID. And I remember Emmett Kading, one of our postdocs at the time, had to, John's group snail mailed us, or FedExed us the sample from Penn State. Then Emma took it to our electron microscopist who fibbed the sample, then drove to the Bay Area, did 2 weeks of quarantine with her brother, and then, brought it up to the advanced light source so we could actually do the imaging, because it's a lot of data. It's almost 800,000 diffraction patterns that then you have to analyze. But the nice thing about this sample is it has electronic structure. So it's a nickel metal lattice. So it's got these little nickel spheres and necks. And so it helps us with the scalar tomographic alignment. So then we know that our vector or 3D spin texture is accurate. And so this is a little movie. You can see, so it's not a perfect structure, but it's perfect for our purposes. And you can see that we can see regions with hedgehogs and anti-hedgehogs, or, topological monopoles and anti-monopoles. Then you can zoom in and you can see pairs of, this took 4 years, okay? So nobody's going, this is a PhD thesis or 2, but somebody has to start, if we're going to be able to look at these in real time, somebody has to start. And then we sort of analyze the full image to see, where did these structures show up and how far apart they were. And so as you might imagine, that if you have a hedgehog anti-hedgehog pair, they can be much closer than if you have a hedgehog or anti-hedgehog. And sure enough, if you do the statistics, yeah, this is gorgeous. Our John Meow's student and our students. Movie. Oh, that is the young student on the project. Arjun, yeah. This is online too. Yeah. It's beautiful. Yep. And, as I was saying, as you might imagine if you've got a hedgehog and hedgehog pair, they can be much closer together, 20 nanometers maybe peak than two hedgehogs or two anti-hedgehogs. And of course, that we had help from Ezio Ayakaka, who's now in Colorado Springs, who did theory to show that this sort of made sense for the type of structure with the spacing, 65 nanometer nickel nanoparticle spacing. So this, at the time, the interesting thing about this is it makes no prior assumptions about the sample, which needed to be made using other techniques. So it's a general method. Then more recently, we did what's an even harder experiment. This also is a 4-year-long effort, which is trying to image the spin texture in a skyrmion sample. And the reason that sample is much harder than the metal lattice sample is the skyrmion sample only has magnetic contrast. Because the other sample had a textures nickel metal lattice that gave rise to the frustrated magnetic texture, but we had the actual metal lattice to do all the tomographic alignments, because when cosmic beamline keeps getting better and better, but the way we had to do these experiments, because we were the first people to, our Strobe was the first group to try and do this, is you have to take the sample out and put it back in as you tilt. So that means you always have to be, you're never right in terms of the axes. So that was the trick. So on the third effort, we finally figured out how to make this measurement right, which was to put in alignment fiducials. So otherwise you have no idea if the magnetic texture you're extracting is real. So the alignment fiducials, so this is little hole, both edges and holes, and this is a multi-layer gadolinium iron sample on a silicon nitride membrane that's a little bit rippled. And in addition, there's stray light. And so all of this complicates extracting the image. But, again, after a 4-year effort, this is the third sample where we finally figured out that we first thought that the edges might be enough to do the tomographic alignment, but it turns out they're not, because they're not perfectly sharp. And when you do extra imaging, you can have carbon buildup. So you have to have other things as well. So we have a master person in charge of our electron microscopy of materials facility. So he was the one who did this, nanofab, and then stuck this onto this, and this is a finder grid, and then stuck that into the coherent microscope. And then we applied the magnetization, this again during COVID, so it's not perfect, but we don't need perfect skyrmions to see if we can image them. We were actually happy enough that to have even imperfect skyrmions, because then we can sort of see what what texture we can see. So these are dipole stabilized skyrmions because they had to survive without a magnetic field, because there was no magnetic field available in the microscope. So first we had to do the, first we have to do the scalar alignment perfectly so we can have people believe, and this is not published yet, so we don't know if they'll believe it, but anyway, I'll show you. And then of course, we compare with simulations as well. And we know the sample structure. Yeah. So, yeah.
Picture. Where is your sample?
The sample is there, and that's a blow up.
Oh.
Yeah. It's crazy. I mean, this, the fibbing at this level is like really, really hard. So Sadi Yazdi is just amazing. He does all our sample prep. Yeah, it's really, because I mean, the whole sample is, this 10 microns, the whole sample is 20 microns square. Yeah.
And is it like, how thick? Like for your techniques, do you care how thick?
Yes, we do care how thick because the X-rays have to make it through. Yes, so but it turns out skyrmion multi-layers that support skyrmions need not be very thick. So it's fine to image in transmission. The X-rays can make it through. This is soft X-rays near the iron L edge, which is about 700 EB, 750 or something. So first, you have to make sure exactly what you're saying. Are you seeing good magnetic contrast? So what you do is you first of all, you add your left and right circularly polarized you subtract them and then you you add them and then you subtract them. And when you add them, you make sure in each 2D image that you're not seeing any skyrmion-like structures, and they only come when you subtract them. So then you're getting the magnetic contrast. And then the next trick is every time you took the sample out, you put it back in a slightly different position. So you have to do something which is called image registration, and you got to move it around. So that this is like a year. But after you do everything right, then, and of course, should have no contrast in the scalar image, because you have a little bit of contrast because of missing wedges, and the silicon nitride membrane was rippled, and that's what you're seeing here on the left. But what I'm showing here is the fact, this is Iona Binney's PhD thesis with help from Ben Scherer, and you see very nice sharp holes corresponding to that. So this took many approaches to learn how to do the adjustments to get a nice sample. And this is if you do it wrong. So here you get a nice multi-layer sample and good holes. In our initial efforts, you could see that the 3 tilt planes are not all the same plane. So the images aren't registered properly. And so then you can't believe, you can see the holes are shifted. So you could not believe the spin texture from that incorrectly image. But after, 3 or 4 years, we can have the 3D spin texture. This was a mixture of stripe domains and skyrmion sample. You can see the holes here. There's a little bit of, you can see a little bit of structure in there, but this is a lot dimmer than in the the main part of the sample. And then of course, as I said, we have to compare with simulations, and these were done by Thomas Fegler. He was a postdoc at ALS before moving to Brookhaven. And so these are what we expect to see in terms of the spin texture. And then here is a comparison of our data with the simulations showing reasonable agreement. We have to do, I have the movies and I forgot to, but is, because it's so uniform throughout and it doesn't have as much of metal lattice texture, it's, yeah. But we can still take a single skyrmion, see as predicted by theory that you should see block skyrmions in the middle layer and nail caps on the top and bottom. And Iona is beginning to try to, depth average, so we can pick out to see if we see some interesting topology. We don't know yet. We're still looking at the images to see if we can see the elusive biskyrmion or the other types of interesting topological structures that people have speculated about. We were not super careful with the sample, so anything could be present, because the field may not have been applied very well. Murnane, yeah. It's a gadolinium iron multilayer fabricated by Eric Fullerton's group on a silicon nitride membrane. It's a dipole stabilized skyrmion sample. And we didn't care, what the sample, we just wanted to show we could image a sample with only magnetic contrast. Yes. Exactly. It's suspended. It very like the one that I showed you for the metal lattice. Exactly the same thing. Let's see if I go back here to the. Yeah, it's literally on a grid, the very same type of grid that we did for the metal lattice sample. There's no, the silicon nitride membrane is not magnetic, so there's no signal from it. Yep, yep. Oh, room temperature, plasmic, yeah.
So all your experiments are done at room temperature.
Yeah. Yeah, we dream about, yeah, magnetic field and temperature, which of course we need, but we don't have, but that's why, we're microscopists, not, yeah, that's why we're developing new methods, not studying, the best Korean sample, yeah.
But in principle, it's possible to do this.
Oh, yeah, absolutely, absolutely. You need to, and of course, the better beamlines, as the beamlines are upgraded, like I'm sure Brookhaven is going to have one, as the beamlines are upgraded, they'll have the possibility of adding in magnetic field and temperature. Absolutely, absolutely. Yeah. Yeah.
Have like, as it is, without this method, otherwise, with other methods.
Oh, yeah, all the other methods work, the neutron, Eric looked at the same sample with the neutron scattering. So we're trying to do it with X-rays because we could also do time resolution, so.
This is like film, right? I mean,
This is a film, exactly, yes, but almost, I guess, MFM can look at the top of the thing. This can look at the 3D structure of this fermion, which might not be uniform throughout the whole material. So that has an advantage over MFM. It can have time resolution, which is an advantage over neutron scattering. And it does 3D advantage over electron and could do higher time resolution. So it has, for some questions, you can do things with this technique, which you can't do with others. Like I said, it ain't published yet. So, yeah. But it was just a heroic effort from Iona and the team from Berkeley and UC San Diego and UCLA. Okay, so with that, I'm hoping oh, sorry, yeah.
Measure and time resolution, or is that just more difficult?
So at the ALS, they run in bunch mode sometimes. So the issue is we can make very bright beams in the EUV that could do time resolution. We've done RMS with time resolution. But in the soft X-ray at the RNL edge, so we've done RMS, dynamic RMS at the M edge. But that spatial resolution would be like 25 nanometers. By going to the L edge, we get to sub 10, which we wanted. That's right. At the LS.
Yeah.
At Brookhaven has time resolution in the soft X-ray region. You have to design a different machine.
How do you achieve it? Like this, how do you design something to have time resolution?
Oh, just pump probe. So for example, you would take a laser, excite the sample, and then probe with X-rays. You just control the pump probe. You do stroboscopic imaging. Yep. Yeah. Brendan will talk about that tomorrow. So with that, I'm out of time. So I hope I gave you some insight into what can be done with X-rays in terms of generating them, controlling their emission, and using them for imaging. And I have to have a big thank you for the group and the collaborators and sample makers who we worked with, in particular our imaging and materials team, the laser team, the spin and charge dynamics team, as well as our collaborators here from CU Boulder, UCLA, UCSD, NIST, Salamanca, some industry, and some recent graduates. And thank you very much for the opportunity to speak and for your great questions. Oh, absolutely. We have a project that is not clear how long it's going to take, but we're trying to show that we have a chance to do, again with Jiang Yao, low dose imaging without killing the biological sample. So the idea is with tachography, you could imagine a sample that's split into two regions, one that's highly scattering and one that's protected you can protect it with a thin film filter. Then you shine your X-ray beam on it, and the interference pattern that's captured on the CCD camera is the interference between the two regions. But the highly scattering region can act as a sort of a heterodyne. So it gives light to interfere with the weak scatter from the sample, whether it's a polymer or a biomaterial. So we're trying to show that we have a chance to do imaging of a live cell at high resolution without killing it. That is going to be several PhDs.
Also study.
I think we would be happy if we could look at any dynamic spin texture. Because that would be, you know, yeah, we're a methods group, so it would, whether that's mutation, a phase transition, or something like that, that would be really cool if we could actually see it happening. See, yes, you know, one of the questions at the resolution, we look at things as, if it's a phase transition, would the nucleation happen at different positions in the material? See all kinds of effects. That would be really nice to.
Phenomenon, like atomic thing to dimension material, do you think it's something feasible now, or is it single layer, like a single graphene or single like transition matrix?
So the single layer, the materials, the 2D materials are looked at a lot. There's a bunch of groups doing RPs, because it's a really beautiful technique. RPs is a beautiful technique for EUV RPs, for looking at their, or even, you know, yeah, transitions, all kinds of.
Yeah, maybe just asking about the skirmion.
Oh, the skirmion part. Good question. Yeah, whether you could look at, say, for example, a magnetically intercalated 2D system and get enough scattered light. Yeah, clearly, if you make it very small, the signal would be very small. But you know, the sources are getting brighter. I'm sort of talking. This is a brain dump. So it would really depend on how delicate the materials are. You know, if they can survive, and if you have a good high brightness and stable beam, so that you, and not have the problem we had, which is a lot of scattered light that was changing as you rotated the sample and made the tomography harder. Yeah. So it's not out of the question.
I think the talk was like really beautiful. The data is gorgeous. With some like skirmion systems, there's discussions about like racetracks for skirmion.
Yes,
like
yes,
that.
yes, yes.
With your time domain information, are you able to like potentially visualize this?
So we haven't done it, but Jeff, MIT Jeff Beach has done gorgeous work on very small skirmions using the Brookhaven synchrotron source. I think that's 100 femtosecond. And so he was able to look at skirmions, you know, being moved around in fields and such. It's really beautiful. He wasn't 3D spin structures, but he could do RMS and he could see the little, yeah.
If I understood the construction and texture correctly, it's like a reconstruction.
Oh yeah.
So if one wanted to think about correlation functions and like pairwise correlation functions of the spin texture, how much should one look into that data? Like, because it's reconstructed, it's not measured correctly.
Correct. Correct. This is kind of why we have to be obsessed with the scalar alignment, because otherwise nobody will believe us. So I think, yeah, this showed that multiple artifacts to do the scalar alignments are needed. So you never, I should never say never, because the other thing we struggled with here was that there was scattered light that was different for as we would, rotate, do the tomographic scanning, and we don't know how much that made it harder. And then, of course, we overcame that with better algorithms and with the additional tomographic fiducials. So, it could be that with the right designed experiment, this could be faster. And yeah.
So like comparison to like sort of theory at this point can still remain a bit more like visual rather than like looking at it exactly.
Oh. Yes, we have just, these images, we just got about a month ago. So we are still looking at the data and trying to compare with, what we can see when we, depth average to sort of see, well, what are we really seeing and does that make sense? But skyrmions are hard to see. So there's a lot of speculation out there. So even though we may not be perfectly validated, this is better than anybody else has been able to do because nobody has done a full field imaging of a skyrmion or even a mixed skyrmion strap domain lattice. So there's a lot that people won't know the answer to because you just couldn't see it before. Yeah. Yes. I think it would be the cost. I mean, you would need a really fancy high magnetic field device near a synchrotron or one of these because we can't make soft X-ray bright enough yet with the laser-based systems. So it's a facility. Yeah. Yeah. And it's just hard to get time on it. So there's, it just depends what the priority is.
Like around 1/3?
Don't. That's the way it comes out.
And that's
Yeah.
because of
Okay, good question. Very good question. And I purposefully didn't bring this up. You remember I asked you, so when do the electrons tunnel? At the peak of the field, all right? Well, I was not telling you exactly the truth because yes, most of them tunnel at the peak of the field, but if they tunnel at the peak of the field, then they move out and then they return. They have zero energy when they return, no harmonics. But if they're born just after the peak of the field, then they move out a little bit, and when they come back, they have energy. And if they're born a little bit after again, they move out and they have a little bit more energy, and a little bit after again, they move out and a little less energy. So you automatically get chirped emission because the electrons that correspond to each energy is defined by their motion in the light field. And so depending on when they're born, the emission comes out at slightly different times.
in order to actually get out of that Attosecond process, you're then compressing it in some way?
I will talk about this Friday because then I'll talk also about a measurement because we shouldn't get obsessed on making attosecond pulses. They're useless. I'm joking. I'm joking. I'm joking. But it depends what you want to measure. Yeah. But I will go into this on Friday.
But if it's femtosecond, then
Yeah.
It shouldn't be an issue. Your sample chirping, it shouldn't be as nearly as much of an issue.
For a lot of, the thing, so for many measurements, for all the imaging I showed you today, it doesn't care. It's static. We're just using the coherence. Brendan will talk about phonons tomorrow. There, he needs maybe 500 femtoseconds of time resolution. Maybe 100 is nice sometimes for very thin samples. And then, but for RPs or for phase transitions or spin manipulation, then you can definitely use, there's a sweet spot where if you kind of compromise on the energy time resolution, you can actually make a better measurement because you can still link it to a particular band. Yeah, and I'll try and explain that. And we can discuss it in detail then. I better let people get some lunch.